Hi, I'm Samin. In this assignment, we learned about Markov chain implementation, which is a stochastic model that describes a series of possible occurrences when the probability of each event is only determined by the state obtained in the precedent event. The first thing that we need to do is to import numpy as p, and then we can test it by creating a one-dimensional array according to the above example. Then we learned how to implement transition matrix to represent Markov chain, which is the matrix associated with the basis change of the vector space. In the first question, we were asked to write a function to return the transition matrix for the following Markov chain given the number of states as an argument with the rules given below. So let's assume we have a restaurant and we have 3 items that we serve, but we only serve 1 item per day. And we can kind of predict what is going to be served tomorrow because there exists a certain relationship, and those relationships are transition probabilities. In other words, every state depends on its previous state. Now we can think of our question in such a way that we have a set of n states and a probabilistic rule to jump to another state every step. We started by making a function called transition matrix that gets n numbers of states as its parameter. Then we generated an n by n array containing zeros to initialize the probabilities corresponding to every state at 0 at first. For the second rule, which says that we fall back to state 0 with probability 0.1, what we did was to assign this probability to the states of the first row and every column up to n. For the third rule, which says if I is at least 1, it goes to state I minus 1 with probability 0.3, but if I is 0, it stays at state 0. We performed this rule by adding 0.3 to the range of 0 to n minus 2 for the rows and the range 1 to n minus 1 to the columns of our transition matrix. For the first condition, which says it will go to state I plus 1 with probability 0.6, what we did was to assign this probability to the locations in the range of 1 to n for rows and the range of 0 to n minus 1 for the columns. For the last condition, which says it will stay at state n minus 1 if it is at state n minus 1 with probability 1, what we did was to assign this probability to state n minus 1 and to increment the probability of the 0 state by 0.3, which we previously assigned to 0.1. Then we returned our transition matrix and tested our function by assigning 10 for the shape of our matrix. As you can see, the result is identical and we have a 2-dimensional array with the required entries. In the second question, we were asked to use transition matrix to learn the probabilities of being in each state after running the Markov chain for k steps. So we implemented a function which, given an initial distribution p0, number of steps k, and a transition matrix tm, it will return the distribution after k steps. We started by creating a function called propagate, which gets p0, k, and tm as parameters, and created an array copy of our p0 object. Then, for each item from the range 0 to k minus 1, we performed a matrix multiplication of our tm and our copy array that we previously made, and then assigned our copy to the result. Lastly, we just returned our copy array and tested our implementation by making a 10 by 10 transition matrix and assigned an array of zeros to our p0 object and assigned value 1 to its first index. After that, we made an instance of our propagate function and assigned p0, tm, and also assigned the parameter k as 30. So now the result will give us the probabilities of being in each state for k steps. Then if we print this instance, the result will be identical to the result below. In the first part of the third question, we were asked to compute how many steps does it take for the probability of being in the final state to be at least 0.5. Firstly, we declared a variable called prop0, and this variable will store a 2-dimensional array of zeros to initialize the probabilities corresponding to every state as 0 at first, Now, once we have made our first step, the count corresponding to that state should become 1. Then we define a variable for our previous state and assigned the start state to it. And lastly, we initialize the number of states to 0. Since we want the probability to be at least 5, using the while loop, we took a variable I and we increased the value of it, and the loop stops when the probability of the last state, which is indicated by -1, is 0.5. Then we can make use of our previously made propagate function, which computes the probability of being in each state after k step, and then assign our probability to this propagate function with initialized values for its parameters, and then increase the number of steps by 1. And lastly, when we print the number of steps, we get 50, which means it takes 50 steps for the probability of being in the final state to be at least 0.5. For the part B of this question, we were asked to convert the above code into a function that computes the number of steps by 50% probability in the final state, which we did by putting the above code into a function called numSteps that gets the size of the Markov chain as its parameter and returns the number of steps. For the part C of this question, we were asked to compute and plot the number of steps required for n ranging from 10 to 40. So we started by importing the matplotlib.pyplot, and after that we created our array with evenly spaced values from 10 to 40. Then we initialized an empty set. In a for loop, we stepped through every item in our array and assigned our previously made numSteps function to k, which represents the number of steps, and then appended the k's to our empty set k step. Then, to plot this, we use our library, which we imported, and called plt.plot number steps and k steps, which represents number steps to be the x-axis and k steps to be the y-axis of our plot. Then we saved our plot using plt.savefig function. For the next step, we plot another graph using plt.semilogy function, which is used to make a plot with log scaling on the y-axis and plots the imaginary part of y versus the real part of y. We passed number steps and k steps as parameters and saved it using plt.savefig function. In the first part of the fourth question, we were asked to write a function that, given a starting state, the Markov chain tells us to move to various random states with some probabilities. So first, we imported numpy.random library and started by making a function called sample that takes transition matrix tm and initial state as 0. Then we needed to create an empty list to append our states to, and we also initialized the shape of our transition matrix, and lastly, we defined a variable for our previous state and assigned the start state to it. To do this, inside of the for loop from the range 0 to 49, we first initialize an array of zeros of size n to initialize the probabilities corresponding to every state as 0 at first. Now, once we have made our step, the probability corresponding to the state becomes 1. And then we implemented a matrix multiplication of our transition matrix and the array that we just created. Afterwards, since the state choice would have to be random, we assigned our state to np.random.choice with range n and appended those states to our empty initialized state list. And last but not least, we returned our states list. For the part B of this question, we were asked to write a function which runs a random walk in the chain for k steps from an initial state S0. The random walk works in the following way. We start from S0 and sample a new state to move to. Then we set that new state to be S0 and sample a new state to move to from there, repeating this until we have stepped k times. This part is very similar to the previous part. The only difference is that it should take the number of steps as parameters, and instead of declaring the range ourselves, we now pass k as a range in our for loop. And everything else is just the same. To test our sample, we assigned values to our parameters and sampled 20 trajectories of the Markov chain and plotted them. The plot shows that almost all the trajectories would have reached the final state by the end. And lastly, we saved the graph using plt.savefig function. In the fifth question, we were asked to use our implementation of sample to estimate hitting times in a Markov chain. The hitting time between state I and j is the average number of steps that a random walk starting from state I takes to hit state j. For this, we will be using Monte Carlo simulation, which has a logic like this. Simulate a random walk with a high number of steps and count the number of counts each state is appearing in our random walk, and if we divide the state frequencies with the number of steps, with the number of steps, we just get the stationary probabilities. Now, this method works if the number of steps is huge, since according to the law of large numbers, as we do an experiment many times, eventually the answer will converge to the expected values, and in Markov chain, the stationary distribution is nothing but the expected probabilities of the given states. So here we simulated a random walk for 1 million steps. First, we need to start with some states. Let's start with state 0, and then we declared a variable called pi, and this variable will store the stationary distribution. At first, we initialized the stationary probabilities corresponding to every state as 0. Now, once we have made our first step, the count corresponding to that state should become 1. Then we define a variable for our previous state and assigned the start state to it. Then inside of our while loop, we took a variable I and we increased the value of it, and the loop stops when it hits 1 million. When we arrive at the current state, we need to increase the frequency of the state by 1. So after the loop execution is done, we just need to divide the frequencies with the total number of steps to get the probabilities. It will take some time to execute this since we're doing it for 1 million times. So the results will give us the stationary probability for the state. For the next step, we are expected to write a function propagate_at_most, which takes an array and a value that should return an array with max value entries, where its entry of the value of the output array is the proportion of the values from array R, which are at most I. To do this, we created the function called proportion_at_most with our parameters and made an empty array called output, and for every items in that range, max value +1, and inside that, for every item in our array R, if j is less than or equal to our item I, we're going to append that to our empty list. Then outside our inner for loop, we append 0 to our list if this expression returns true. Otherwise, we will append the proportion of the length of our nr and r array and return the output. After that, we test our function, and we can see the results are identical to the results above, and also we plotted the function, and in the rest of the question we computed the theoretical probability using propagate function for every value of k between 0 and 2000. That was all. Thank you so much for listening.